In the vast expanse of our solar system, orbiting the ringed giant Saturn, lies a world of ice and mystery. This is Rhea, Saturn's second largest moon. Although you're more likely to have heard of its larger sibling Titan, Rhea is a fascinating place in its own right and harbours many secrets and wonders. Ice cliffs, hundreds of meters high, an internal structure that defies scientific models, and the enigmatic discovery that lingers around this moon that's equally as strange as the thing we didn't find. It's time for this lesser-known moon to step out from its larger sibling shadow. Let's learn all there is to know about Rhea. I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today on a voyage of discovery to the Saturnian system and the moon Rhea, to see what scientists have discovered there and to discover its wonders for ourselves. Rhea was discovered on the 23rd of December 1672 by Giovanni Domenico Cassini, the Italian astronomer who made numerous contributions to our understanding of Saturn and its moons. Named after the Titan goddess Rhea in Greek mythology, this moon has been a subject of fascination for astronomers and planetary scientists for centuries. Let's start with the basics. Rhea is the second largest moon of Saturn, after the mammoth Titan. With a diameter of 1,528 kilometers, it's roughly half the size of our own moon. If we were to place Rhea next to Earth, it would stretch from London to Warsaw. Rhea orbits Saturn at a distance of about 527,000 kilometers, completing one orbit every 4.5 Earth days. It's locked in a synchronous rotation with Saturn, meaning the same side always faces the planet, a common feature among large moons in our solar system. The surface of Rhea is one of the most reflective in our solar system, with an albedo of 0.7. This means it reflects 70% of the sunlight that hits it, appearing bright white against the backdrop of space. This high reflectivity is due to its composition. Rhea's surface is primarily made of water ice. But this doesn't make it a featureless ice sheet. Far from it. The moon is heavily cratered, telling a story of ancient impacts and a long, violent history. The largest of these craters, named Mamaldi, spans an impressive 480 kilometers in diameter, about the distance from Paris to Amsterdam. These craters aren't just scars on Rhea's surface. They are windows into the moon's past and composition. Observations have shown that the bottoms of some craters appear darker than the surrounding terrain. This could indicate that impacts have excavated material from beneath Rhea's bright surface, possibly exposing darker, amorphous water ice and impact melt. In this photo, you can see a crater in the southern hemisphere of Rhea, surrounded by bright ejecta. But one of the most intriguing features of Rhea is its system of bright, wispy streaks that crisscross its surface. These were first observed in detail by the Voyager space probes in the early 80s, but their true nature wasn't understood until the Cassini mission provided high-resolution images decades later. Initially thought to be deposits of frost or ice, these wisps were revealed to be ice cliffs, some hundreds of meters high. They are likely the result of tectonic activity in Rhea's past, where the icy crust fractured and some sections were thrust upward. These features give us clues about the moon's geological history and the processes that have shaped its surface over billions of years. But Rhea's mysteries don't end at its surface. In 2010, data from the Cassini spacecraft led to a surprising announcement. Rhea appeared to have a tenuous atmosphere or exosphere. A small amount of gas around Rhea is expected, but it was unexpected that there is enough to be measurable. The detected atmosphere consisted primarily of oxygen and carbon dioxide, with the oxygen being about 5 trillion times less dense than Earth's atmosphere at sea level. While incredibly thin, the mere presence of this atmosphere raised intriguing questions about its origin and sustainability. One theory suggests that the oxygen is produced by the decomposition of water ice on Rhea's surface when it's struck by ions from Saturn's magnetosphere. The carbon dioxide, on the other hand, is thought to be the result of organic molecules on the surface being oxidized by the oxygen in the exosphere. This discovery made Rhea the first moon known to have an oxygen atmosphere other than Jupiter's moons Ganymede and Europa. It also opened up new avenues for research into the complex interactions between Saturn's moons and the planet's powerful magnetosphere. Rhea's exterior is fascinating, but what about its interior? Let's dive deeper, literally. While we can't directly observe what's beneath Rhea's icy surface, scientists have used various methods to infer its internal structure. Based on Rhea's average density of 1.236 grams per cubic centimeter, which is only slightly higher than that of water, we can deduce that Rhea is composed primarily of water ice, about 75%, and a smaller fraction of rocks, the remaining 25%. Rhea has often been described as a frozen, dirty snowball due to this structure. This puts Rhea in stark contrast to moons like our own moon, which are primarily rocky bodies. When Cassini visited Rhea, the probe's instruments also provided valuable data about Rhea's composition. Spectroscopic observations confirmed that water ice is the dominant component of Rhea's surface, but they also detected the presence of other materials. One surprising discovery was the detection of carbon dioxide trapped in the surface ice. This finding suggests that Rhea's ice isn't pure water, but contains other compounds, possibly including complex organic molecules. Due to its higher moment of inertia, most scientists believe that Rhea is not differentiated into layers. Instead, it is thought to be a homogeneous mix throughout, with the exception of its core. Some scientists challenge this model though. In 2006, a paper was released in the journal Icarus that suggested that Rhea might have a layer of liquid water under its surface, a subsurface ocean. While this idea is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus, it's an intriguing possibility that future missions might investigate. The presence of such an ocean would have significant implications for Rhea's potential habitability and of the conditions necessary for liquid water in the outer solar system. Rhea's interior contains mysteries, but one of the puzzling features of Rhea is its shape. While many large moons and planets tend towards a perfect sphere due to their own gravity, Rhea is noticeably non-spherical. It's slightly flattened at the poles and bulges at the equator, a shape we call a traxial ellipsoid. What's strange is that Rhea's shape doesn't quite match what we'd expect based on its rotation rate. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure, with denser material concentrated away from its center. Now, let's talk about one of the most exciting moments in Rhea's recent history, the Cassini mission's close flybys. The Cassini spacecraft, a joint project of NASA, ESA, and the Italian Space Agency, spent over a decade studying the Saturnian system, including several close encounters with Rhea. The closest of these flybys occurred on the 11th of January 2011, with Cassini passing a mere 76 kilometers above Rhea's surface. The last close flyby was on the 9th of March 2013, when Cassini passed just 997 kilometers above Rhea's surface. This close approach allowed the spacecraft to capture incredibly detailed images of Rhea's cratered terrain and gather valuable data about the moon's composition and determine it does not have an internal magnetic field. These flybys provided us with our best look yet at Rhea's surface features. They imaged a landscape dominated by two types of terrain, heavily cratered regions and younger, smoother plains first shown in earlier Voyager missions. The heavily cratered areas we mentioned earlier are thought to be extremely old, possibly dating back to the early days of the solar system. These ancient surfaces provide a record of the intense bombardment that occurred in the solar system's youth. The smoother plains, on the other hand, are likely the result of a resurfacing event, such as from material ejected from large impact events. This material would have fallen back to the surface, filling in older craters and creating smoother regions. But perhaps one of the most intriguing results from the Cassini mission was what it didn't find. Prior to Cassini's arrival, some scientists had proposed that Rhea might have a system of rings. This idea was based on unusual measurements of electron densities around Rhea made by Cassini in 2005. However, despite careful searches during its flyby, Cassini found no evidence of rings around Rhea. This non-detection doesn't completely rule out the possibility of some kind of debris disk around Rhea, but it does make it much less likely. Another intriguing aspect of Rhea is its place in Saturn's complex system of moons. Rhea orbits Saturn in what is known as the E-ring, a diffuse ring of ice particles thought to be supplied by the cryovolcanic eruptions from Enceladus. While Rhea itself doesn't seem to be geologically active like Enceladus, its position in this ring means it's constantly interacting with these ice particles. Although Rhea is in the extremities of the E-ring, beyond where it is dense, over time this interaction could affect Rhea's surface properties and contribute to the moon's bright appearance. As we reflect on what we've learned about Rhea, it's clear that this moon, often overshadowed by its more famous siblings, is a fascinating world in its own right. From its heavily cratered hemisphere to its relatively smooth side, from its tenuous atmosphere to its place in Saturn's complex system of moons, Rhea continues to intrigue scientists and spark our imagination. But our exploration of Rhea is far from over. Many questions remain unanswered. What is the exact nature of its interior structure? How has it evolved over the billions of years since its formation? Could it harbor simple forms of life in a hypothetical subsurface ocean? These questions and more await future missions to the Saturnian system. While there are currently no planned missions specifically targeting Rhea, the moon is likely to be observed by any future spacecraft sent to study Saturn and its moons. As we conclude our journey to Rhea, let's take a moment to appreciate the diversity of worlds in our solar system. From the scorching surface of Venus to the icy plains of Pluto, from the towering volcanoes of Mars to the potential subsurface oceans of icy moons like Enceladus, our cosmic neighbor is filled with wonders waiting to be explored. Rhea, with its icy surface reflecting the distant sunlight, stands as a testament to the beauty and mystery of our universe. As we continue to explore and learn, who knows what secrets this distant moon may yet reveal. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the Saturnian moon Rhea. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.